Hi, welcome back to the lecture series on theory of this major theory with course code MMTC 202. So today in this lecture we will see that every uh, every Borel measure, every translation invariant Borel measure is a scalar multiple of Lebesgue measure. As we know that the Lebesgue measure, if lambda is a Lebesgue measure, which is a which is a function from this collection of all subsets of Rn to 0 to infinity. It's a Lebesgue measure on Rn. Is a Lebesgue measure on Rn. Then this lambda, it's lambda is translation invariant. It has these properties actually. Lambda is translation invariant. That's the first property, and second property, it's translation invariant, and second property, it's a regular Borel measure. Lambda is a regular Borel measure. It's translation invariant. It's a regular Borel measure. Now, in the next theorem, we will see that if mu is a measure, on Rn, this theorem is very important. It's a measure on Rn such that mu is translation invariant. Mu is translation. It's any measure on Rn with this property. It's translation invariant. It's translation invariant. Second property, it's also a Borel measure. Borel measure means the measure of a compact sets or finite. Mu of every compact set is finite. Mu is a Borel measure. Mu is a Borel measure. Then we show that this mu is actually it's equal to c times lambda. It is some constant times lambda. So that means every translation invariant Borel measure is actually the Lebesgue measure. It's some scalar multiple. So let's state this theorem. State this theorem here. Let mu be a translation invariant Borel measure on Rn. Let mu be a translation invariant Borel measure on Rn. Borel measure on Rn. Borel measure on Rn, then there exists a constant c. Then there exists a constant c belongs to R such that mu of A is equal to c times Lebesgue measure of A, not for every subset of Rn, but for every Borel set, for every Borel set A, for every Borel set A. Actually, it's true for every subset. That will do. That I will keep as an exercise for you. But here I will prove this equality. Mu is equal to c lambda on the collection of all Borel sets. Okay. So we try to construct a function f which is additive on Rn and also continuous at 0 in each variable separately. Then we will use the previous theorem which states that this function f which is having these two properties is actually c times that we already done. So for this, let's fix some notations. For each x belongs to, for each x belongs to R, for each x belongs to R, for each x belongs to R. Let's denote this Ix. It's equal to, the phi set, empty set, if x equal to 0. That's a notation. No? If x equal to 0 and its value is equal to, this Ix is equal to, it's 0 to x if x is positive. It's interval 0 to x open on this side. If x is positive and this Ix is equal to, it's 0 to x if x is positive, but it's x to 0 if x is negative. X to 0 if x is negative. And for also for every point of Rn, also for every x equal to say x1, x to n tuple in Rn, we define a signum of x. Okay, we define this function that's called a signum of x. It's equal to, 1 if the product of these, if the product of the coordinates of this vector, it's equal to 1 if the product, of the coordinates of this vector, this n tuple I runs from 1 to n, is non-negative, if it's greater or equal to 0, and we'll take its value as -1 if this product, xi is negative. So where this x is the n tuple, x1, x2 up to xn. If the product of the entries of this n tuple is negative, then the value of the x is equal to -1 under this function signum. And if the product of the entries of this vector is greater or equal to 0, then I will take signum of x equal to 1. So for instance, let's for n equal to 3 suppose. Let's take n tuple. Say we take this vector x equal to say 1, 2, 5. So what's the product of these entries? It's a positive number. So here signum of x is equal to, 1. And if I will choose, they say x equal to say -1, 2 and 3, the product is negative. So here the signum of x is equal to -1. And if suppose is one of the entry equal to 0, say one of the entry equal to 0, then the product is 0. But for non-negative, whenever product is greater or equal to 0, the function is the value of the function, the value of the signum of x is equal to -1. So here this value, this signum of x is equal to 1. Its value is 1, sorry, if the product is non-negative. Okay, so for n equal to 3, if I will choose these 3 tuples, then I can calculate the signum of these tuples by first obtaining the product of the entries, whether this product is negative or is positive or it's a 0. So that's the definition of this signum function. Okay, so let's since in that statement of the theorem use a Borel measure, and it's also translation invariant. And so assume now that mu is a translation invariant. Mu is a translation invariant Borel measure on Rn. Okay, I've defined a function that I already discussed it with you. We try to construct a function, define a function f from Rn to R by f of x1, x2, so on xn is equal to the signum of this vector x into the measure of this product of the interval, say ix1, ix2. So it's this ix1 cross ixn. So this is subset of Rn actually. Okay, because ix1 is subset of ix1 is either 0 to x1 or x1 to 0, or itself it may be the empty set. So this is the product of n copies of these semi-closed intervals actually. So it will be the subset of Rn. So mu is defined on the subsets of Rn actually. So this mu, okay. So this can be written as this. Can write this as signum of x into mu. I will write this as product. I runs from 1 to n I xi. So if any xi is 0, then that ixi will be equal to the empty set. Therefore, the product of these n copies of these ixis would be equal to the empty set, because the one of them is the empty set. So here I will write. I will explain it here. If we have two cross product of two sets, say if we have cross product of two sets, say one is A and second is the empty set B, then the product is always the empty set. Okay. So if any xi is 0, then the corresponding ixi will be equal to the empty set. Therefore, this product is the empty set. In that case, its value is 0. So, but in case the each xi is either positive or negative, then these sets they are just semi-closed intervals, and it is the product of the n copies of semi-closed interval. Either some of them may be left semi-closed, some of them may be right semi-closed, depending on these xi's whether they are positive or negative. And it says signum of x. What's this x? Where this x is the n tuple actually. Okay, it's the n tuple. X is equal to x1, x2, x. So this is the function from Rn to R, because signum of x is either positive or negative, and the measure is always a non-negative number. So this output, it's the real number. It's either negative or positive. So this f, it's a function from Rn to R. It's a function from Rn to R. And we show that this f is additive in each variable. First, we verify that first we verify that f is additive in each variable separately. Okay, so let's choose this point. Let's choose x equal to, let's choose this x equal to, say, x1, x2, so on up to xn belongs to Rn. So we try to prove its additive first variable such that this x is equal to, say, x1 is equal to a plus b, where a and b are the real numbers. We show that it's additive in each variable. So we need to show that it's additive in the first variable, also in the second, and all the variables. So without loss of generality, I will prove it's additive in the first variable. The other variables follows on similar lines. The additive nature of this f will follow on the similar lines. Okay, for the other variables. Okay, I will prove it only for the first variable. It's additive in the first variable. So that's why I have written this x1 as a plus b, and we show that this f of x1 means f of a plus b. Then these are fixed numbers. I fix these numbers. It's equal to f of a. Sorry, it's f of a x1 x2 It's f of a x to xn plus f of b. Okay, we show that this. So for this, we considered certain cases on A and B. Let's choose this. Let's have case one here. Case one. In case one, it's if A is positive, if A is positive, B negative, and A plus B is positive. Okay, and you choose another case: A positive, B positive, sum is also positive. A negative, B negative, sum is also negative. But A positive, B negative, but and sum is negative. That's the other case. Okay, and say A negative, B positive, sum is positive. A negative, B positive, sum is positive. So there are several cases actually. So I will explain this case only. The other cases you can do yourself, and they actually follow on similar lines. Okay, but you tried those cases as well. This because that's very important for you to prove all the cases. Okay, so let me try to explain this case. If A is positive, B is negative, A plus B is positive. Okay, so you can see this interval. Let's you can see this interval here. It's here 0. So A is positive, A is somewhere here. A plus B is positive, but A plus B must be less than A because you are adding a negative number to A. So A plus B is positive, but it's somewhere here. This is A plus B, okay? This is A plus B. And B is negative, okay? B is somewhere here. B is negative. Now look at this difference. 0 to A, interval 0 to A minus A plus B to A minus A plus B to A. Look at this difference. It's equal. So 0 to A means this portion. Okay. Sorry, it's this whole portion. 0 to A. This is A plus B. So 0 to A minus A plus B to A. It's equal to 0 to A plus B. It's equal to 0 to A plus B open. Because you are excluding A plus B also from this 0 to A. So this is trivial, okay? This is trivial. And let's take this notation. Let S is equal to. Let's define the number S, which is equal to the signum of this n minus 1 tuple x2, x3, so on up to x. So this may be negative or positive depending upon the product actually. Okay. So I will denote this by S. The values of S are either plus 1 or minus 1. And let's denote this interval. Let's choose this interval. I runs from 2 to n. 2 to n, not from 1 to n, because the first interval, because the first point x1 have been written as A plus B, and we'll show that it is additive in the first variable. So that's why I will fix the remaining. I will fix the notation for the remaining variables for x2, x3, xn. It's I xi. I runs from 2 to. So this S is the signum of x2, x3, so on, xn. This I is the product. I runs from 2 to n, I xi. And clearly this is true. This I have already explained. Clearly we have this 0 to A minus A plus B to A is equal to this it's equal to 0 to A plus B, 0 to A plus B. And this thing is now trivial. This A plus B to A cross I this is equal to this is equal to so I can write this a plus b comma a as because you are actually translating the interval b to 0 by a actually. So it's actually like this. You can write this as a a plus b 0, a plus b 0. Okay, a plus b 0 cross I. So you are adding this a to b comma 0, it will be a plus b to a. Then this can be written as this can be written as can write this as a. So this is a, and the rest of the components are equal to 0 plus b0 cross I. This this is simple. You can easily verify this. They are equal. Both are actually sets. You can prove in terms of sets. They are proving this. This is a subset of that one, and this one is a subset of this. So that's very simple. This is a plus b0 cross I. That's equal to a 0 0 0 plus b comma 0 cross I. Actually, this I is the product of the n minus 1 copies, and this is here the this is the first copy. This is the closed interval, a semi-closed interval, and that's the product of n minus 1 semi-closed interval. So it will be the product of n semi-closed intervals. So now you can verify this. If we choose any point here, say any n tuple here, then the first entry of this tuple belongs to this interval, and the remaining entries of that tuple will be in, say the second one will be in ix2, third one will be in ix10, and so on, and the nth one will be in ixn, because I is the product ixi. I runs from 2 to n, but first one is in this is here. So that can be written as a plus, okay? And then you can see that that one, because you need to write this as an as a sum of two sets actually. So for this, I will write this a as the n tuple, and this is the point of Rn. Now you are adding this point to this subset of Rn. So that's simple. That is simple. You can check it out. That's if you choose say x here, then that x uh, then that x is the n tuple which first entry belongs to this set, and the remaining that x2 so on up to say y2 so on up to yn belongs to I, but y1 belongs to this, and that y1 is equal to a plus z1, where z1 lies between b and 0, and the remaining actually you are having this this is actually x, this whole x is equal to y1 y2 so on yn. Then you can this y1 can be written as a plus some point, and, so let's try to verify it, okay, without creating any confusion here. So actually I need to verify this one, or can do this. I need to verify this a plus this a plus a plus interval b to 0, interval b to 0 cross I is equal to a 0 0 cross B 0 cross I. That's that I need to verify. So let's verify this. Verify this. So I choose y here. Y belongs to this set a plus interval b to 0 cross I. So this y is some n tuple, and say y is equal to say y1, y2, so on up to yn. So this is true if and only if y1 belongs to this a plus interval b to 0, and the remaining n minus 1 tuple, it belongs to I. And this is true if and only if this y1 it's equal to a plus z1, and these y2, y3, so on up to yn, they belong to I. So this y1 is equal to a plus z1. Okay, a plus z1. So what's now y? Y is actually equal to this one. So this is true. Now this is true if and only if this is true. Our y is now equal to, what's y? Y is equal to y1. That's equal to a plus z1, y2, so on up to yn, which is equal to, which can be written as a 0, so on up to 0, plus now this one it's equal to z1, y2, yn, which belongs to this one. It belongs to, you can see this one, it belongs to a 0, 0 plus this one. Where is this this point z1, y2, so on yn? Z1 is in this z1 belongs to a, this z1 belongs to b comma 0. So this one, this belongs to b comma 0. So I will write it in the next page. So this belongs to a 0, 0 plus this z1, which is in b to 0. I think is it b to 0? Yes, b to 0 cross I. So that proves this result. This y it belongs to a plus b comma 0 cross I if and only if this y belongs to a 0, 0, 0 plus b 0 cross I. Okay, so that proves this result. This we have verified now. Okay, now since mu is translation invariant, since mu is translation invariant, so therefore mu of this b comma 0 cross I is same as mu of some element of Rn, that's a 0, 0 plus b0 cross I. So mu is translation invariant means mu of a plus some set, mu of a plus the set is equal to mu of the set. Mu of the element plus set is equal to translation invariant. Mu of element the point of the set is here a 0, 0, which is the point of Rn, plus the subset of Rn is equal to the mu of the subset of Rn. So that's translation invariant, and which is equal to this one. What's this a 0, 0, 0 plus b0 cross I? It's equal to A plus B, A plus B, uh, A cross I. Okay, because this sum is equal to A plus B, which is already proved here. This this one, this sum A plus B comma 0 cross I actually, or you can say, oh, it's, it's A0 plus the interval, uh, A000 plus that one B cross B comma 0 cross I, it's equal to this one A plus B comma 0 cross I, which is equal to A plus B comma A cross I. Okay, so this one. So this is actually equal to this A plus B comma A plus B comma then A cross I. So because this mu is translation invariant, mu of the point of the set plus the subset of the set where this mu is translation invariant is equal to the mu of the set. Okay, translation invariant property of mu. So now we see this now let's find these now this f of a x2 so on up to xn plus f of b x2 xn. We show that this is equal to f of a plus b x2 x3 so on up to xn. But what is this f of a? It's equal to the signum of this point. Okay, as gn of this a x2 xn into the mu of the product. It's say I a cross I x2 cross I xn. That's the definition of f. Plus plus f of b is it's by definition it's signum of the vector, which vector is here b x2 xn into mu of this ib cross I x2 cross I x n, and that's equal to, since this a is positive, therefore the product ax2 x3 so on up to xn is same as the product x2 so on up to xn. So that means signum of ax2 so on up to xn is same as signum of x2 x3 so on up to xn, because the both are positive simultaneously, both are positive because a is positive. As a is positive, that means the sign that means the sign of a into x2 into x so on up to xn is same as the sign of x2 x2 into x3 into so on up to xn. So if the product ax to so on up to xn is negative, then the product x to x3 so on up to xn is also negative. So which means that the signum of ax to x3 so on up to xn is -1, and the signum of x to x3 so on up to xn is also -1. So I mean to say that this signum of this n tuple ax to x3 so on up to xn is same as the signum of this n-1 tuple. Why? Because a is positive. It will not change the sign of the product x to x to one up to xn. If we multiply that product x to x to one up to xn by this positive number, but then but that one, if I will find this product a times x to so on up to xn, it will give the signum of that vector, but by removing this one it will give the signum of x2 so on up to xn, and there is no change in sign, so the signum of both the vectors must be same. So I will write this as it's actually signum of x2 so on up to xn. Okay, then this one it's equal to mu of I a, mu of I a this is IA is the interval. I will write this as an interval actually, because this A is positive. So what's IA? A is positive. So by our notation, A is positive, so this IA is equal to 0 to A cross, and this and the remaining product is denoted by capital I. That notation is already fixed. Okay. Now plus. Now look at this one. Now second term. This b is negative, so that means the product that means the sign of the product will change. If the product b x to so on up to xn is negative, then the product x to x to so on up to xn will be positive because b is negative actually. And if the product bx2 so on up to xn is positive, then the product x2 x3 so on up to xn will be negative. So that means since the signum has only two values, plus 1 or minus 1, so which means that if the signum of this vector is plus 1, then the signum of the x2 x3 so on up to xn is minus 1. If the signum of this n tuple is minus 1, then the signum of this n minus 1 tuple is plus 1. So it will be minus times. It will be minus times. It will be minus term. So signum of this is will be minus times signum of the n minus 1 tuple. Just sign will change. It's minus times signum of x2 so on up to xn into mu of ib. What's b? B is negative here. So ib means 0 to b. 0 to b. And cross this product is denoted by capital I. Okay. But this signum of x to x2 is it's denoted by s, and that's also s. That's the notation. So this is equal to s times so s times now I will write s is the common factor, s times this mu of 0 to a cross I minus mu of b to 0 cross I. Okay, b to 0. But mu of b to 0 cross I is equal to this already done here where mu of b comma 0 cross I is equal to mu of a plus b comma a cross I. Okay, so this is equal to s times mu of 0 to a cross I minus mu of this is here a plus b a cross I. And that's equal to s times it's equal to mu of since the measure of the these sets are actually subsets of some compact set in Rn, so they are always finite because mu is a Borel measure. Here we are using the Borel measure property actually. Yeah. So this is equal to mu of the difference. Mu of the difference means 0 a cross I minus a plus b a cross I. Okay. And this one is equal to s times mu of. What's the difference? This difference already calculated somewhere where this is here. Okay, I think at the beginning this one. Okay. Okay. It should be somewhere. It should be somewhere where I have verified this. This is after fixing this notation. Okay, this one. Okay, this one 0 to a minus a plus b to a is equal to 0 to a plus b. Okay, this one. This is here actually. Okay. this is here. This is here. This one, okay. This one you can see this one 0 to a minus a plus b to a is equal to 0 to a plus b is equal to 0 to a plus b. So let's see this. This is equal to 0 to a minus a plus b to a. That's equal to 0 to a plus b. It's equal to mu of 0 to a plus b cross I. Cross I. Because 0 to a minus a plus b to a is equal to 0 to a plus b. Therefore, 0 to a cross I minus a plus b to a cross I is equal to 0 to a plus b cross I. You can now easily verify this by taking this product with I. This it will hold. This I is fixed. So we are changing only the first components of these set of n tuples. Actually, 0 to a minus a plus b to a. So the rest is the same cross I. Okay. Now this one, you can see this one. This is what's S? S is by definition. So S is the signum actually. So I will write this in the next page. This is equal to what's S? S is signum of x so on xn into mu of 0 to a plus b. Is it 0 to yes 0 to a plus b is positive. Okay, it's 0 to a plus b cross I. But this signum of x2 it's same as the signum of a plus b, because a plus b is positive, so this will not affect the sign of the product. Whether you take the product of these n minus 1 or you take the product of these n entries, or you take the product of these n minus 1 entries, because this is positive, so this will not change. This will not change the sign of the product, whether you take the product of n numbers or you take the product of n minus 1 number. These. And here this is equal to mu of what's this? This is actually I a plus b, and these are this capitalize ix2, ix3 up to ix n. Okay. So this is the signum. It's actually, this is by definition, this is equal to f of a plus b, then x2, so on up to xn. Okay, so this proves the additive property. Therefore, f is additive in first. Therefore, f is additive in first variable. In this case, Similarly, on similar lines, we can show that this f is additive in first variable. F is additive in first variable. In all the cases. In all cases. On similar lines, we can see that f is additive in each variable, separately. So next we show that f is continuous at 0 in each variable separately. Next we show that f is additive. F is continuous at 0. Additive is already done. Additive part is already done. F is f is continuous. F is continuous. F is continuous at 0 in each variable, in each variable separately. So without loss of generality, without loss of generality, we prove that it is continuous. It's continuous at 0 in the first variable, in the first variable. That is limit say x1 approach to 0, f of x1 x2 so on up to xn is equal to f of 0 x2 so on up to xn. Okay, so we prove this. First, we show that. First, we show that this left-hand limit. We prove that the left-hand limit exists, and the left-hand limit is equal to f of 0 x to so on up to xn. So let's choose ak with respect to k. We choose let this ak let this ak increases to 0. ak increases to 0. So this is here 0, and this is here 0. Okay, and this is the sequence ak which increases to 0. Okay, ak is increased, ak approach to 0. This ak it increases to 0. Okay, so we show that the f of ak x to x3 so on up to xn will approach to f of 0 x to so on up to xn. So this x1 is approaching to 0, so it will approach to 0 on we have to take the two approaches, and right hand approach and the left hand approach. So let's take first this right hand approach. So ak is increasing to 0. This left hand approach ak is increasing to 0. So by taking this approach, we see that this set ak is a negative number, so I can take this set, this interval cross I. Now since this ak is increasing to 0, so this set obviously this set will decrease, and this will decrease to the empty set. You can easily verify this, because whenever ak is increased to 0, this will be the empty, and therefore the product ak cross I is equal to empty, where this I is this I is the product, because rest of the elements are fixed. It's a product I runs from 2 to n. Okay, so you can see this ak comma 0 cross I, it will decrease to 5. So decrease means that this is decreasing sequence, because ak is decreasing, increases to 0, so this will be decreasing sequence. So suppose ak is first, say it's say -1, then it's minus 0.5, then it's minus 0.3, minus 0.7, minus 0.8, minus 0.9. So it will approach to 0, but you can see this interval is decreasing by approaching ak to 0. So this is actually the decreasing sequence of sets with respect to k, with respect to ak. This is decreasing, and you can see the intersection of this this sequence k runs from 1 to infinity. The intersection will be the empty set. That's a simple calculation. So that means this one, it will decrease the empty set. this will decrease to the empty set. Okay. So if it decrease to the empty set, then what will be its measure? That means measure of this set ak to 0 cross I will also decrease to 0, will also decrease to 0, will also decrease to 0. So that means the limit, that means the limit of this mu of ak0 cross I is equal to 0. This limit k approaches to infinity. K approaches to infinity. This limit is equal to 0. Which implies that the limit k approaches to infinity, the signum of ak x2 so on up to xn into mu of I can write this mu as mu of this ak comma 0, it's equal to ak comma 0 cross then ix2 so on up to ixn is equal to 0. This implies the limit k approach to infinity. What is the signum of? Because this signum is either plus 1 or minus 1 and the limit of this is 0. So that means limit of this plus 1 times or minus 1 times the same mu of this ak0 cross ix2, ix3 so on up to ixn, because I is ix, the product ixi, I runs from 2 to n. So this is also 0 because you are multiplying this limit with a factor that's either plus 1 or minus 1. So it will not affect the limit. It will not affect its limit because its limit is 0. So it will remain 0. But this one now, it's actually this f of ak x2 so on up to xn is equal to 0. So that means this limit this ak approach 0 f of ak0 so on x2 so on up to xn is equal to f of 0 x2 xn. Similarly, or you can say it's actually it's actually now this it's the right hand limit. I can write this as limit this a limit this this is say x1 x2 so on up to xn. This x1 is approached to 0 minus from left hand side. This limit is 0. Similarly limit x1 approach to 0 from the right hand side, f of x2 so on f of x1 f of x1 x2 up to xn is equal to f of 0 x2 xn. So thus limit is equal to the value of the function in the first variable. Thus limit x1 approach to 0, whether you take left approach or right approach, xn is equal to f of 0 x2 up to xn. So therefore f is continuous in the first variable at 0. Therefore f is continuous at 0. Therefore f is continuous at 0 in the first variable. In the first variable. On similar lines, on similar lines, we can show that f is we can see that f is continuous at 0 in each variable, in each variable. So this f is additive and continuous at 0 in each variable. Therefore, there exists some constant c such that f of x1, x2, so on up to xn is equal to c times x1, x2, so on up to x. This is a product now. Here it's product. Okay. C times x1 into x2 into up to xn. So this is true now. Okay. So obviously this C is a positive number because this C is a positive number. Clearly C is positive. So clearly C is positive. Verify it. Okay. This C is not negative. It's positive. Verify it. This is very simple. You can easily verify it. This is a positive number. Now let's take the any member of this product of n copies of semi-closed intervals. Now let AB is equal to product this I runs from 1 to n AI BI product of n copies of semi-closed intervals where this minus infinity less than AI less than BI less than infinity. Okay, for each I. So then this A can be written as by using the this A is equal to it's equal to, because you are actually translating this some semi-closed interval by this vector. Actually, it's equal to plus product I runs from 1 to n 0 to bi minus. This is very simple. This is very simple. This is I can easily verify this. Choose any point x here. You will see that x must be lies here. So this is equal to this one. It's equal to a1, a2, so on up to an plus this product I runs from 1 to n. What's this? The notation for this is I bi minus ai. Okay. Now we try to find mu of A. Now, what's this mu of A? Mu of A is equal to mu of this set, but mu is transition invariant, so it will be the mu of this one. It's mu of product I runs from 1 to n I bi minus ai. Okay. And that's equal to, that you can see this is equal to signum of b1 minus a1 up to bn minus an into mu of the product I runs from 1 to n I bi minus ai, because this value of this is equal to 1. Okay, as they are all positive number, therefore product is positive. So I am just multiplying this factor this number by 1. Actually it's C. But no, what's this? But then this one, it's equal to actually it's the definition of function. It's f of b1 minus a1 b2 minus a2 bn minus an. That's the definition of function. And this one, it's already proved that this is equal to C times b1 minus a1 Bn minus An. But what is this? This is actually the Lebesgue measure. This is equal to C times Lebesgue measure of the product of these intervals. Actually, product of these Ai, Bi. So thus this mu of A is equal to C times Lebesgue measure of A for all A belongs to the member of the semi-ring. But this will give mu of A is equal to C times Lebesgue measure of A. This is here equal to this is equal to this is equal to C times Lebesgue measure of A, because A is this the product. Okay, this C times A of A for every member A belongs to the, which is a Borel set. And this one, this last equality, it follows from the theorem 15.10 on elephants, which we have already discussed in one of our lectures. Okay, so this mu of A is equal to C times the Lebesgue measure of A for all A belongs to the Borel set B. For every Borel set A. Okay, A belongs to the Borel algebra actually. A is a Borel set.